Hello everyone, I'm Chris McIntosh and I help teach the statistics courses. Today I wanted to emphasize a few points about null hypothesis significance testing, or as it's commonly abbreviated, NHST. This is out of the Navarro text in chapter 9. So research hypotheses differ from statistical hypotheses. Research hypotheses are a substantive, testable scientific claim. They're related to the study overall and not just a statistical test. There's some examples in Navarro's text. Listening to music reduces your ability to pay attention to other things. Intelligence is related to personality. Intelligence is speed of information processing. Those are all research hypotheses. A statistical hypothesis is mathematically precise. It corresponds to claims about the data generating mechanism. There are examples in the Navarro text of statistical hypotheses. If people are guessing, the probability of guessing a correct answer is 0.5. If people aren't guessing, the probability is greater than 0.5. The statistical hypothesis should be related to the research hypothesis. The example in the text was about the existence of ESP. The research hypothesis is ESP exists. The statistical hypothesis, the probability of a correct answer is greater than 0.5. Excuse me. A statistical test is a test of the statistical hypothesis, not the research hypothesis. A study needs to be well designed for the link between the research hypothesis and the statistical hypothesis to be sound. And this is pretty crucial for the validity of any claims you're making based on statistics. Statistical hypotheses consist of the null hypothesis and the alternative hypothesis. The null hypothesis, or H0 or H0, is some form of there is no difference, relationship, or effect. So it's going to change, the wording is going to change a little bit based on what test you're using, but it's going to be some form of there is no difference. The alternative hypothesis, or H1, sometimes I've seen it with HA as a subscript, but I'm going to be using H0 and H1 throughout this whole semester. Some form of there is a difference, a relationship, or an effect. So the goal of NHST is to demonstrate that the null hypothesis is probably false. This is somewhat counterintuitive. The trial of the null hypothesis, H0, the null hypothesis is assumed to be true. The researcher needs to prove that the null hypothesis is probably false. NHST doesn't actually generate evidence that the alternative hypothesis, H1, is true. This is part of why it's kind of a convoluted and difficult process to understand. There are two types of possible errors when deciding whether or not to reject the null hypothesis. A type 1 error is when you reject the null and it should not be rejected. The null hypothesis is actually true. A type 2 error is you fail to reject the null when it should be rejected. The null is actually false. And this table comes out of the Navarro text. You can see on the left is reality, H0 is true or H0 is false. And then you can see your decisions. If H0 is true and you retain the null hypothesis, that's the correct decision. But if H0 is true and you reject the null hypothesis, then you make a type 1 error. If H1 is false and you retain H0, that's a type 2 error. Or if H0 is false and you reject H0, that's the correct decision. The main consideration in NHST is controlling for type 1 error. The probability of a type 1 error is called alpha. Alpha is the Greek lowercase letter. This is also called the significance level of the test. The three common levels for alpha are 0.05, 0.01, 0.001. Those are what you're going to mostly see in medical research. I've mostly seen 0.05 and 0.01. The probability of a type 2 error is called beta. Beta is the Greek lowercase letter beta. We usually think about power instead of beta. Power is 1 minus beta. And there's a table in the Navarro text listing out your alpha and beta levels with your null hypothesis. We calculate a test statistic to help guide our decision about the null hypothesis, H0. A sampling distribution helps us know what values of the test statistic cause us to reject the null hypothesis. Selecting a test statistic and sampling distribution is beyond what we will discuss right now. You're just going to be learning the tests mostly. We will discuss specific test statistics later in the course. There is a process for testing the null hypothesis, and this varies slightly from text to text, but this four-step process is the basic steps. Step 1, state the null and alternative hypothesis. Step 2, establish the criteria for rejection, the alpha level. Typically, we're going to say alpha 0.05 for everything in this course. Step 3, calculate the test statistic. Step 4, make a decision about the null hypothesis. Use this language when deciding about rejecting the null hypothesis. There are only two possible choices. Reject the null, which is when your p is less than your alpha, you're going to reject the null, and fail to reject the null when your p is greater than your alpha. Memorize these two statements. Those are the only two statements that will be useful for you in this course. Avoid other terms to describe this decision. There are subtle implications with other terms, and people knowledgeable about statistics might take issue with them. Incorrect terms, do not use these in this course, is accept the null, accept the alternative, the null is supported, the alternative is supported. Just because of the way these tests are structured, any decisions based on an NHST test is not valid. And we will see later on, there's another way to look at some of these things and calculate things that we can make a statement about supporting or the null or the alternative, but it's not with an NHST test. So your two options for NHST are reject the null or fail to reject the null. Use this language talking about the p-value of a test. The p-value of a test is the probability of seeing the current data if the null hypothesis is true. A low p-value means the data are unlikely under the null hypothesis. A p-value lower than alpha level is required to reject the null hypothesis. And you want to memorize those concepts. Avoid other terms to describe the p-value unless you understand the nuance behind it. And Navarro has a nice description of what the p-value means. And here I pulled this out of the Navarro text because this was actually, I think, really good to understand, and it's not something that's commonly taught. A very brief digression is in order at this point regarding the word significant. The concept of statistical significance is actually a very simple one, but has a very unfortunate name. If the data allow us to reject the null hypothesis, we say that the result is statistically significant, which is often shortened to the result is significant. This terminology is rather old and dates back to a time when significant just meant something like indicated, rather than its modern meaning, which is much closer to important. As a result, a lot of modern readers get very confused when they start learning statistics because they think that a significant result must be important, an important one. It doesn't mean that at all. All that statistically significant means is that the data allows us to reject the null hypothesis. Whether or not the result is actually important in the real world is a very different question and depends on all sorts of other things. Don't confuse statistical significance and clinical significance. Statistical significance happens when p is less than alpha. It indicates the data are unlikely if the null is true. It's used as justification to reject the null hypothesis. Significant does not mean important in this context. The p-value is affected by sample size. Large sample sizes may lead to small p-values and may make a small result statistically significant. Small sample sizes may lead to large p-values and may make a large result not statistically significant. Clinical significance is usually measured using the effect size. We'll talk more about that later. An effect size is calculated using differences in means and is not affected by sample size. A small effect size may indicate a result is not clinically important. A large effect size may indicate a result may be clinically important. You need to gauge clinical significance based on domain knowledge. P-value and effect size are not directly related. It is possible for a small study with a low number of participants to not be statistically significant, even if there is a large effect size. The large effect size may indicate possible clinical significance. A large effect size may indicate further investigation is needed, even if you don't have statistical significance due to a small sample size. It looks like that's about the end of what I had prepared for this. And I will just tell you that I differ from the way Heavey has presented clinical significance. These effect sizes are pretty important, and I think I'll probably emphasize this in later lectures. But even on a small study or a quality improvement project, getting the effect size is useful, because then people can design larger studies based on the effect size observed in a small project. So don't discount something when it's not statistically significant, when it has a moderate or large effect size. That effect size may indicate that there really is something going on that should be investigated further. So we'll probably talk more about this later. Have a good week.